So we are going to do today, I hope to finish the chapter 0, this one, okay, and maybe to start to the chapter 1, dealing with the Brown motion, okay, definition, construction, and so on. I will see. Okay, so we will be in the part concerning martingales in continuous time. So I repeat, I don't light on because if I film and light, okay, it doesn't work. But now it's better because I have a big board, okay, so to do maths it's perfect. Martingales in continuous time. So this topic is very large. It should be possible to do a course only in this topic, okay, during 40 hours, okay. So I will do it in 3. So you can imagine that it will be like a summary, and typically I will insist on the things we are going to need later, and only on this part, okay. So it will be the martingales in continuous time. To start with the definition, and after I will do some comments. And we are going to see some rules of computations concerning martingales, and to see on the space of continuous martingale with continuous trajectory, but the good way to equip this space with a norm in order to make it flexible to handle in what we are going to do after. Okay? So definition. So as usual, you have a probability space that will be fixed in the whole chapter, and I will consider a filtration, okay, that is just an increasing family of sub-sigma algebra of calligraphic A. Okay? Definition of a filtration. FT on A, filtration. And as I have said during the previous session or 2 sessions ago, we are going always to suppose that the filtration are complete in order, for example, to have things like if y is ft measurable and x equal to yp almost surely, I want x to be also ft measurable. Okay, so complete filtration, meaning that it contains the negligible sets as defined previously. Okay, so let's see the definition. We'll have 3 statements in one. Okay, so an adaptive process MT, T belonging to R plus. So first of all, I want to be adapted, and adapted to what? To my filtration. Okay, I have a natural filtration at the beginning of the section. Okay, I want to be adapted to FT. So an adapted process MT, T belonging to R plus, with values in L1 is. So we are going to see 3 things: martingales, sub-martingale, and super-martingale. So is I will write it this way: martingale, sub-martingale, or super-martingale, if for all t greater than s, okay, in R plus, I have the following. So 3 definitions, so 3 conditions. So martingales, if the conditional expectation of MT given Fs is equal to Ms, This is the definition of being a martingale in continuous time. Okay, and that's why here I suppose my process to be in L1 because I want to be able to consider conditional expectation that was defined for random variables in L1. Okay, so the conditional expectation of MT given Fs is equal to Ms. Okay, sub-martingale, the conditional expectation of MT given Fs is greater, for sub it's greater than Ms. So Ms is less than this conditional expectation. Less than this conditional expectation means that I am a sub-martingale, and the super martingale case is this one. Okay, so this is the definition of a martingale, a sub-martingale and a super martingale. So something I suppose that you have already seen a little. Okay, and if not the case, you have this one that is coming from the definition of conditional expectation. So I repeat that L1 here is in order to give sense to all these conditional expectation. Okay. And if you want to have an intuition about the notion of martingale, it means that the best approximation of MT given the information I know at time S, that is a time before, has to be Ms. Okay, so this is the intuition behind the notion of being a martingale. Okay.
Could you repeat the intuition, please?
Yes. I have given to you an interpretation, okay, in L2 of conditional expectation as projection or as best approximation of. So the intuition here is that if I consider this conditional expectation as the best approximation of MT knowing the information at time S, this best approximation has to be Ms. Okay? So S is the time before T. If you have less information than the one at time T, if you want to approximate MT, the best way you can do is to use Ms. Okay? So what you see from this definition is that a sub-martingale plus a super-martingale implies that you have a martingale because you have the double inequality. Okay, that we go. If MT is a martingale, what can you say about this mapping? What can you say about this mapping if I am a martingale here? It's a constant. And why you have a constant? But it comes from the definition, of course. You can take the expectation on both sides in the equality, and you know that the expectation of the conditional expectation is just the expectation of the random variable. Okay? So this is a constant because if I take the expectation of the conditional expectation of MT given Fs, from the definition of being a martingale, this is the expectation of Ms. And from the property of the conditional expectation, I know that the expectation of the conditional expectation is equal to the expectation of the random variable. This is by property of the conditional expectation, the expectation of MT. So a martingale is constant in expectation. Okay? So a sub-martingale is increasing in expectation and a super-martingale is decreasing in expectation. Okay, taking the expectation in the conditional expectation inequality. Okay, but this one we know. Okay. So to show you the example of something that is a martingale, that is in fact a canonical example, we can prove, but it is a difficult result that I don't have the time to see, but just to show you an example. I say that if x belongs to L1, okay, of omega AP, if I define MT this way, MT that is equal the conditional expectation of x given Ft, I said that this process is a martingale. So you have a fixed random variable and you consider successive approximation, let's say. Okay? And if you do this, this process is a martingale. So MT is equal to the conditional expectation of x given MT is a martingale. How to do? I just have to check that the definition is okay in this situation. Okay. So I have to prove this. Okay, for T greater than S. Okay. So to show why I have this example. If T is greater than S, I am interested in the conditional expectation of MT given Fs, and I want to prove that it is equal to Ms. The tower property, yes, exactly this one. So I replace, of course, MT by its definition. Okay, so MT is equal to the conditional expectation of x given Ft. So this is MT, this one, by the definition of my example. And I have to do the conditional expectation of this one given Fs. And now I agree with you that we use the fact that we have a double conditional expectation. We have a double conditional expectation with Fs that is included in Ft. And in the lecture notes, it's exactly what I have called the tower property of conditional expectation. If you do the conditioning with respect to a big sigma algebra, then with respect to a little one, it's like you do the conditioning with respect to the little one directly. So it's the tower property in the list of properties fulfilled by the conditional expectation we have seen together. And so I have exactly what I want, because by definition of this process is none other than Ms, and so you have proved that the conditional expectation of MT given Fs is equal to Ms. Okay, so you have a martingale this way. Okay. And in fact, more or less, all the martingales have this form. It's possible to find such an X that is a kind of representation of martingales. Okay? They won't need this result in this course. Okay, so I have this one with a canonical example based on the tower property of conditional expectation. So now we are going to see rules of computations for martingales. Okay, we have special things that works for martingales and that we are going to prove. We are going to prove that you see that the proof that are very short, in fact, but will be useful in the computations we are going to do together after. Typically, in the next chapter, the one motion we are going to deal with will be a martingale, and so we will be able to use these rules of computation in this situation. It's something that we will do. Okay? So, two rules of computations with martingale. So, are you okay with the definition? For most of you, it's something that you have already seen next semester. Okay? So, I have this one. Okay, proposition 0.5.3. So let MT belonging to R plus be a square integrable. A square integrable just means that MT belongs to L2. So I have something that is a little bit greater than what I need in my definition. In my definition, I need to be L1. Here, since we are going to consider conditional expectation of the square, I need it to be in L2. Okay? So let MT be a square integrable martingale. In fact, when I want to compute the conditional expectation of MT minus MS square given Fs, so when T is greater than S, in fact, the conditional expectation of the square of the difference will be the conditional expectation of the difference of the square. Okay, so I have a kind of simplification here that is just the conditional expectation of mt square minus ms square given fs. And typically, why this result is interesting? Because I remove the square from the parentheses to put it in each term, let's say. So it's something that is not true in general, of course, because in general you develop the square and you obtain something with a double product, okay? You don't have here. And here, typically, the way we are going to use this result is that if we do the sum of such term here, that if the times are well chosen, you will have simplifications between the terms of the sum, because you will have here the difference that you will be able to simplify instead of having the square of the difference, something you can't do. So how to prove this? Very simple. What can I do? In general, I have something that seems to be a little bit more complicated than this one. I start from this one in order to obtain this, and for this one, I can't do anything instead of developing the square and see what happens. Okay? So, the conditional expectation of mt minus ms square given fs is equal to the conditional expectation of mt square minus 2 mt ms plus ms square given fs. I just developed the square. And now, of course, we are going to use the properties of conditional expectation and the fact that my process is a martingale. For the first term, I have to do nothing because it's exactly the first term I want here. Okay, so I use the linearity of the conditional expectation. I have the conditional expectation of mt square given fs minus 2 times the conditional expectation of mt ms given fs and plus the conditional expectation of ms square given fs. And keep in mind that I need them to be in L2 if I want to give sense to each conditional expectation. What I need to have inside the conditional expectation is something that is in L1. That's why I consider here the process to be with values in L2. For this one, what can you say for the last one?
Expected value?
No. Expected value is when I have independence. I don't have independence here. It's just ms square because ms square is fs measurable. Okay? And when I am fs measurable, my conditional expectation is myself. So this is ms square because ms, and so ms square is fs measurable. Okay? for this term here?
Minus 2ms
So I can remove what I know from the conditional expectation, that is the things that are Fs measurable. Here I am in the situation where MT is in L2, MS in the L1, so the product is in MT in L2, MS in L2, so the product is in L1, by Cauchy-Schwarz inequality. So I can remove from the conditional expectation the term that is Fs measurable, that is this one, and I obtain minus 2 times ms, conditional expectation of mt given Fs. And for the moment, I have used only the properties of the conditional expectation and the fact that my process is adapted. So it's here that I will use the fact that I have a martingale. The conditional expectation of mt given Fs is just ms. So here I have ms, and so if I summarize what I have obtained, I have the conditional expectation of mt square given Fs minus 2 ms square plus ms square, that is minus ms square, and I can write the following, because ms is Fs measurable, I can write it this way to obtain exactly what I want. So the conditional expectation of the square of an increment, let's say, is just the conditional expectation of the increment of the square. I repeat that in a few minutes you are going to see an example where this kind of simplification, okay, allow to do computation in a better way. Are you okay? So, not complicated, just use the definition and the basic properties of the conditional expectation. Okay. So I keep this result in mind, okay, that will be used in two results. I erase this. Something that is not very far from this one. That is another rule of computations. It is what we call the orthogonality of the increments of a martingale. So it's proposition 0.5.4. Okay. So I suppose that I am in this situation here. I suppose that T4 is greater than T3, greater than T2, greater than T1. In fact, I have put street in the lecture's note, but it's not that necessary here, in fact. I don't think so. No. So suppose that you have this, with this one that is positive. And I say that in this situation, okay, the expectation of MT4 minus MT3 times MT2 minus MT1, okay, is equal to 0. So suppose that in general you will be in this situation here. You will be in this kind of situation. You will have T1, T2, T3, T4. You consider MT4 minus MT3 that are, okay, the variations of the martingale on this little interval. The other one that is the variations of the martingale on this interval. If you consider the expectation of the product, you obtain 0, meaning that you are orthogonal in L1. Okay, the expectation of the product is 0. Once again, the proof is very short for this result. So of course, yes, I don't have written the hypothesis. So in the framework of proposition, the preceding proposition, I have the same kind of hypothesis, 0.5.3. Okay, if I have this, then okay, so my hypothesis is that I have a square integrable martingale. If I am in this situation, I have the orthogonality of the increments here. So, of course, if I have a martingale, okay, I will need to compute at one time a conditional expectation or something like this. Okay. So the idea is to express this expectation as the expectation of a conditional expectation. Okay. But the only thing is to choose which one in order to obtain the result I want. Okay. So I repeat that I want to compute conditional expectation because I have a martingale, and in the definition of a martingale, the conditional expectation, okay, is very important. So this expectation, I want to write it as the expectation of a conditional expectation. But for the moment, I don't know the sigma algebra I will use for the conditioning. What can you put here? Well, in fact, if I see my statement, I have what? I have ft1, ft2, ft3, ft4.
ft1.
So if you take ft1, ft1 is the smallest. Why not? Let's try. So if I use ft1, that is the smallest. I have ft1, ft2, ft3, ft4 this way. Now what can I do with this one? Not that much. Not that much, because the only one that is ft1 measurable is this one here. But I can't remove the whole product here, or the whole term, from the conditional expectation, because mt2 is ft2 measurable. That is not necessarily ft1 measurable. So why not? But a priori it doesn't work to do like this. So I can try to develop and so on, but I won't be able to remove a lot of random variables from the conditional expectation. The only one I will be able to is mt1.
I'm sorry, I don't get it, because whenever we use an example, we always say s inferior to t. So why and t1 is inferior to t2? So I don't get your point of it not being of mt2 not being ft1 measurable.
Yeah, of course. You have ft1 this way, and ft2 this way. Okay? So, if you are measurable with... Are you okay? You have a filtration. You have a filtration, so you have an increasing family of sigma algebra. So, if you are measurable with respect to ft2, it means that the preimage of any Borelian belongs to ft2. Okay? But if you belong to ft2, a priori, it's not necessary that you belong to ft1. You may have a preimage of a Borelian that is this one, for example. So to be ft2 measurable doesn't imply that you have ft1 measurable. If you are ft1 measurable, you are ft2 measurable. If you increase, okay, the notion of sigma algebra, okay, you will relax the hypothesis of being measurable. You will have more random variable that will be measurable if you increase the sigma algebra. Because, come back to what I say. I said that to prove that a random variable is measurable, the preimage has to belong to the sigma algebra. I said that if my preimage belongs to ft2, a priori I don't know if my preimage belongs to ft1. But if my preimage belongs to ft1, I am sure that I belong to ft2. So ft1 measurable implies ft2 measurable in this situation, not the converse. Okay?
Yeah, but I misread the... It's because it's f, filtration is ft and not fs, so I guess I misread it.
So here, okay, I repeat that. Why not? It was an ID.
So ft4?
ft3, or yes, why not? Okay, ft3. I can also take ft2, it works also, but ft2. FT2, it works also with exactly the same argument. But you say FT3, let's take FT3 because it also works. So in this situation here, what are the random variables that are FT3 measurable? I have this one, and this one. Okay? In particular, this term. So I can remove it from the conditional expectation. So I can write this one as the expectation of MT2 minus MT1 that I remove from the conditional expectation times the conditional expectation of MT4 minus MT3 given FT3. Okay? I just remove the term here that is FT3 measurable. Do you agree? Just basic property of conditional expectation. And now to conclude, here once again, for the moment, the only thing I have used is the fact that my process is adapted. I will need to use the fact that it is a martingale. It is a martingale, so what is this conditional expectation? Zero. It is MT3 minus MT3, 0. It's the definition of conditional expectation. If you take the conditional expectation of MT4 given FT3, you obtain MT3. So this term is 0. And you have exactly what you want. Yeah. If I come back to the definition of the conditional expectation, you have T4 that is greater than T3. So the conditional expectation of MT4 given FT3 is equal to MT3. Okay? So I have this. So when I have a martingale, okay, I have orthogonal increments and I have this nice property for the computation, the conditional expectation of the square of increments. Okay? And now we are going to use this result in order to prove a result. So a result that will be important for us in the chapter 2, okay? Because we will use it in order to prove the unicity in the decomposition of an Ito process. So for the moment, I don't know what is an Ito process, okay? But we are going to define it, and the fact that the decomposition related to this definition will be unique, will be a consequence of the result we are going just to see now. Question?
Quand on dit Martingales de paire intégrale, c'est que chaque unité est de paire intégrale.
Ouais.
Okay.
All the MT are in L2. Just in order, huh? If you want these terms to be well defined, you need that the expectation of the product is in L1. Okay? So you need that each of them, or one condition to allow this is to impose that each of them is in L2. Okay? So I erase the board here, and we are going to prove, I repeat, a result that we are going to use in the chapter 2. So I erase this. So I state the proposition, and after I will erase the board in order to do the proof. Okay. So we are going to consider a particular martingale with a particular form, and we are going to prove that if a martingale has this very particular form, it is necessarily indistinguishable with 0. The unique martingale that will fulfill the condition we are going to write is the martingale 0 in the sense of indistinguishability, and it's a result that will help us to prove the unicity in the decomposition of an Ito process. Okay, so let's see the statement. So let MT T belonging to R plus be a square integrable martingale, so meaning that both preceding proposition we are going to be able to use them. So let MT be a square integrable martingale. such that, so we impose for it a very particular thing, okay, such that there exists what? There exists a stochastic process, phi t, belonging to L2 of omega time 0 capital T, okay, fulfilling, so there exists such that, fulfilling by the fact that mt is in fact equal to the integral between 0 and t of phi of s ds for t between 0 and capital T. So let mt be a square integrable Martingales such that there exists a stochastic process in L2, measurable in L2, fulfilling mt is given by the partial integral of this stochastic process, and we have already seen together that if my process is in L2, here I have a random variable, okay? If I impose to be in L2 prog, I know that here I have something that is adapted to the filtration, something we have seen during the previous session. So mt is equal to the integral between 0 and t of phi of s ds for t between 0 and capital T, and then the probability of the set of the W belonging to omega such that for all t belonging to 0 capital T, mt is equal to 0. This set has a probability equal to 1. So let mt be a square integrable Martingales such that there exists phi t belonging to L2, fulfilling mt is the process that is the partial or the integral depending on the upper bound of this process. Then on 0 capital T, my martingale is, with the definition we have previously introduced, indistinguishable with 0. Okay? So it's what I want. The probability of the set of the W belonging to the universe such that for all t I am 0, this probability is equal to 1. Meaning, I repeat, with the definition previously introduced, that the martingale is indistinguishable with 0 on the interval 0 capital T. Okay? So we are going to prove this. We are going to see that we are going to use this result. So first of all, in general, okay, I have said to you that to prove indistinguishability is something that is not that easy, because you have here, in fact, the probability of an intersection to prove, okay, to be equal to 1. But we have a situation we have seen together where to prove that something is indistinguishable with another process is easier, let's say. Which situation? We have seen different definition of equality together. To be equidistributed, to be a version of, to be indistinguishable. Two definitions. With the fact that indistinguishable implies to be a version of, implies to be equidistributed. Okay? And there are a case where to be a version of and to be indistinguishable are equivalent. Yes, when the trajectories are continuous. So if the trajectories of my process are continuous, it works. Okay? It's the case here. Even we are a little bit more. We said that the trajectories of M on 0 capital T are continuous. And in fact, we have a little bit more than this. the trajectories of my process M are continuous on 0 capital T. Knowing the fact that MT has a particular form. It's not an arbitrary martingale, okay? It's this one. So how to prove this? You have several ways to prove. In fact, I am a little bit more than continuous. Maybe. So you have two ways to do. You can consider a sequence Tn in 0 capital T that converges, okay, and to prove that M of Tn converges toward M of the limit. Okay, it's one possibility to do. And it's possible to do this, okay, applying, in fact, the dominated convergence theorem to this one. It's one possibility to do, but it's not the way I will do. You have an integral depending on the upper bound. What can I do? Linearity in what? So the dependence is in the upper bound. You don't have the integral between 0 and a plus b, that is the integral between 0 and a plus the integral between 0 and b. The integral is linear in my process here, but not linear in the upper bound. Okay? Yeah? Cauchy-Schwarz inequality, in fact. Why? If I consider mt minus ms, supposing that t is strictly greater than s. If it's not the case, okay, I invert. I can always suppose this, okay, because I have an absolute value. What is this one? By its the absolute value of the integral between s and t, f of u du. Okay? I have this one. So your idea is to use the Cauchy-Schwarz inequality. So you can use it. It's not stochastic calculus. To apply the Cauchy-Schwarz inequality, I need to have the integral of the product. Okay? So by Cauchy-Schwarz inequality, what can I say? By the integral of the product is less than what? The square root of the integral between s and t of 1 square du, square root of the integral between s and t phi of u square du. I have this one, okay? This is Cauchy-Schwarz inequality. The integral of the product is less than the square root, the product of the square root of the integral of the square. Cauchy-Schwarz inequality. What is the first term? I have the integral of 1 between s and t. So here, it's the square root of t minus s. And what happened for this one? Keep in mind that I have an hypothesis and my process phi is in L2 of omega times 0 capital T. So this one is less than the integral between 0 and capital T of phi u squared du with this one that is finite P almost surely, because I know that the integral, the expectation of the integral of the square is finite. This is the meaning of being in L2 of omega times 0 capital T. So it means that this one is finite, so you have a number here that is finite P almost surely. And so, if S and T are close together, so this one will be small, and so this difference will be small. So it's not a mapping that is Lipschitz because you have a square root here, but it's a mapping that we called, I don't know if you remind, Eulerian. It's like Lipschitz, but with a power instead of. If you don't have the square root, okay, you have a mapping that is Lipschitz, okay? If you put the square root of any kind of power, you have something that is a little bit restrictive than Lipschitz. What is this one? But for sure, I have the continuity. And in fact, I have a little bit more. I have also the uniform continuity directly from this one. So my trajectories are continuous. Okay? If T and S are close together, then this one will be small, and so this one will be small because this one is finite P almost surely. Okay? So my trajectories are continuous, and according to the remark of your friend here, if I want to prove that MT and 0 are indistinguishable, it is sufficient to prove that MT is a version of 0. So to prove the result, we only have to prove that MT is a version of 0, that is, for all T belonging to 0 capital T, MT is equal to 0 P almost surely. Something that is a priori simpler to prove than to prove that the probability of this intersection is equal to 1. And what I have written on the board here is a consequence of the fact that my trajectories are continuous. So indistinguishable is equivalent to be a version of in this situation. Okay? And this is the definition of being a version of 0. MT is equal to 0, P almost short. So for the moment I have used nothing. The only thing I have used is the integrability of this process and the form of my MT. I don't use for the moment that I have a Martingale. Okay? So it's what we are going to do now. To prove that MT is equal to 0 almost surely here is in fact equivalent to prove that the expectation of MT square is equal to 0. Okay? Because you know that when you have a random variable that is positive, expectation equal to 0 is equivalent to be equal to 0 P almost surely. And here I have a square, so we have something that is positive. So I have to prove equivalently that the expectation of MT square is equal to 0. Okay? Ouais.
Je vais sélectionner avec l'intégrale.
MT square?
Un MT carré, oui. Et on peut sélectionner l'égalité de Johnson, peut-être.
Le carré, oui, c'est Cauchy-Schwarz avec le carré. Jensen.
Ouais.
Ouais, pourquoi pas, on essaye. So the idea is to say, okay, just I replace and see what happens. Okay? So if I replace and see what happens, I obtain this one. Okay? And your idea is to say that do more or less the same thing that I have done here. No, it was your idea to say that the integral, the square of the integral will be something that will be less than the product of the integral of the square. It's what you have in mind or not? More or less? More or less? So I can give a bound to this one. Okay, this one is less, I can write it this way, I can write it that it is less than t time the integral between 0 and t phi u square u with an expectation before. Jensen, Oshisha, c'est ce que j'utilise là. Bah, si tu n'as qu'une fonction aussi, là c'est le cas, tu as 1 en fait.
Ouais.
Le carré de l'intégrale est plus petit que l'intégrale du carré. I know that the expectation is okay because I am in L2, but to prove that it is equal to 0, I have a bound here, but for fixed t, okay, I have just a bound that is, I can say that mt is bounded, for sure, huh, because I have this. So these terms are bounded uniformly in T. I have this. It's not what I want. I want to prove that they are equal to 0. Un truc plus précis ou... Ah, bah, je vais voir si je continue sur mon idée à moi ou sur la tienne. So a priori, not by, you are going to see that in fact below I will do this, but not directly, because if you do this, okay, nowhere you use the fact, and it's a very important hypothesis in my statement, okay, I don't have to forget that I have a martingale here, okay, I have a martingale. And what we have seen from the previous proposition is that when you have a martingale, the increments are orthogonal. And the idea will be to make appear increments from this one. So, to say what? To say that if I consider I have my interval 0t, okay? We are going to consider a subdivision of this interval. Let's say, for example, a subdivision of step size 1/20 over n. So I have something like this. Until, okay, so I have a subdivision of step size t over n. And the idea will be to express mt by using increments on this subdivision. That is the difference of the value of the martingale over the little intervals of my subdivision. Why I do this? Because I know that the increments are orthogonal. So mt is written this way. The sum of terms of this form, m, let's say t k plus 1 over n minus m c k over n. And if I do this, my k starts from 0 and finish at n minus 1. Why I do this? Because I have properties concerning the increments of a martingale we have seen previously, and I want to use these properties. Okay, so you have a diagonal simplification with these terms. You have, it's clear for everybody that I have this one? A priori, here, I obtain, since I have diagonal simplification, I obtain mt minus m0, but m0 is equal to what? To 0 for sure, because mt is defined this way. Okay, so I have mt minus n0 that's equal to this one, and I can express mt using increments. Okay, mt is written using increments. And now, if I am interested in the expectation of mt square, it is just the expectation of the square of the sum. The sum that is square. Okay? If you have understood, the destiny of small n will be to go to plus infinity. Consider a subdivision that is with a very small step size. So I have expressed the expectation of mt square as the expectation of the square of the sum. Okay? But from the previous proposition, when I develop the square of a sum, I obtain sum of the square plus other terms that are products of elements of this type, but with different indexes. But knowing the fact that my increments are orthogonal, if I consider two elements of this form with different indexes, if I take the expectation of the product, I obtain 0 from the previous proposition. And so, in the case of a martingale, the expectation of the square of the sum will just be the expectation of the sum of the square. Okay? So from the preceding proposition, from proposition 0.5.4, my expectation, the expectation I am interested in is just the expectation of the sum of the square. I put the square inside the sum from k equal to 0 to n minus 1. I have this. I repeat, because the square of a sum is the sum of the square plus the products of terms with different indexes. And you have, in fact, the expectation of the product of increments on disjoint interval from the previous proposition. We have proved together that this expectation is equal to 0. That's why it only remains the sum of the square, the expectation. Okay? Clear for everybody? Okay. But it will simplify a lot the things, because keep in mind that I have a particular form for mt. Mt is an integral depending on the upper bound. Okay? So I can write it as square of integral tk over n, t k plus 1 over n, phi of s ds. And now we can use your ID, your Jensen or Cauchy-Schwarz. But here, because instead of having a fixed bound, 0t, we are going to have bounds depending on n, okay, with a distance between the bounds that is small, that is t over n, and for big N, okay, this distance goes to 0. So now we are going to use Cauchy-Schwarz inequality, as exactly I have done previously. Okay, you can write it here 1 times phi. Okay, and I obtain from Cauchy-Schwarz inequality the expectation of the sum from k equal to 0 to n minus 1 of what? So I have a square here, so I have just the difference of the bond that is just t over n, and the integral between t k over n and t k plus 1 over n of phi of s square ds. The Cauchy-Schwarz inequality I have previously used. The square of the integral of the product is less than the product of the integral of the square. Exactly what I have written here. Okay, the integral of one square between the bonds is just equal to the length of the interval. And now it's finished because I can remove t over n from the sum. So I have t over n before, and then I have the sum of these integrals, but using, so integrals between 0 and this one, integral between this one and this one, and so on, and using shall relation for integrals, okay, I have just the expectation of the integral between 0 and capital T, phi square yes. From my hypothesis, I know that phi is in L2 of omega times 0 capital T, so I have something that is finite. And when n goes to plus infinity, this term goes to 0. And at the end, what I have proved that the expectation of empty square is equal to 0, because it is less than something that goes to 0. What?
It's not small t.
It's not small t where?
On the final integral.
Yeah. Yeah. Well, if you want, but capital T works also because you have something that is positive inside. I agree that. To be totally correct, I have this one that is less than the same thing, the thing I have written. In both cases, okay. So T is fixed, so you can write it this way. It's a better upper bound this way. But you can put capital T as I have done previously, change nothing, huh? Because if you are less than the integral between 0 and t, since you have something that is positive, you will be less than the integral between 0 and capital T. What? So, this one? So, the way is that I have a square outside the sum, I put the square inside, it's this one that you don't understand. Okay? I know, you have a square. So, just say what happened. If you have the sum of the square, okay? I can write it this way. You have, let's say, I can write it this way. AK plus 1 minus AK, okay, and you do the square of this one. Okay, you do the square of this one. Okay. If I develop the square, I obtain what? I obtain the sum of the square, okay, plus, write it this way, 2 times the sum I strictly less than j between n minus 1 and 1 of something like this. Okay? It's the way I develop the square of a sum. You have double products inside. So, if I come back to my situation here, if I take the expectation equal to the expectation of this term, that is exactly what I write in here. And I said that in the case of Martingale, when you take the expectation of this one, you have the expectation of all of these terms that is 0 from the proposition 0.5.4. Okay? So this is the idea. And it's nice thing because, okay, when I do computation, to pass from this one to this one is nice because after I will use, okay, here the shell relation, for example, or previously. So I don't have such a term when I deal with Martingales if I take these terms in expectation. Okay? If I am not a martingale, I can say this one to this part if I have this form, but I have to handle this one, and a priori I am not able to conclude. Are you okay with what I have done? So, when a square integrable martingale may be written as the integral depending on the upper bound of the stochastic process in L2 of omega times 0 capital T, this martingale is indistinguishable with 0. And you will see, okay, that it will be after the holidays, that what we will call an Ito process will be what we will call the stochastic integral. You will have a stochastic integral term plus a Riemann integral 1. If I want to prove that my decomposition is unique, meaning that if two are equal, the stochastic integral terms are equal and the Riemann integral terms are equal, the result we are going to use is this one. Because from one part you will have the stochastic integral terms that will be Martingales. For the other part, the Riemann integral terms that are exactly the form I have in my statement here, that has to be equal, and if they are equal, 0, okay, necessarily. So I will have the unicity, but I will come back on this point later on. Okay? So I have this one, and really the keystone of my proof is to think about the subdivision, but in order to introduce increments. Then to see that I can pass from the expectation of the square of the sum to the expectation of the sum of the square. Okay? Okay, so if you don't have some question, I will finish with the part concerning martingales. So you have something that is very, very small in this course concerning martingales, okay? And typically, this is probably the big main difference with the course of the triple MEF. In the triple MEF course, okay, they spend more and more time on martingales. Typically, they introduce the notion of stopping times for martingales and so on in order to obtain more refined result for this one. And I won't do this in this course, okay, because I will be in a situation where it won't be necessary for me to know more than this on the martingale. But it's a big theoretical gap, okay, but I did only this one in order to follow the chapter as I have built them, okay, in this course. And typically, the result we are going to see now, that is a big theorem, that is called the Doob inequality for martingales, okay? It's something that I won't be able to prove because I don't have all these tools, okay? And if I remind, okay, Bernard de Meyer in the course of the triple MEF does this proof. We'll admit it, but what will be important for us is to understand what is the interest of this result for what we want to do later on. Okay, we are going to work on spaces of square integrable and continuous martingale, and the idea is to be able to equip this space with a norm that it is easy to handle, not a complicated one, a nice one, let's say, in order to make the computation of norms very, very easy. Okay. So I state the theorem that I will admit, and even I don't have the proof in my lecture's note because, okay, I will need more and more on martingales in order to be able to do. Okay. Maybe you have a reference somewhere, say at the end of the chapter you have a reference, but whatever, it's not necessary for my course. So may I erase everything? I erase everything. we are going to state a need, and it will be the only time in this course where I will use this result, what we call the Doob inequality. Now, intuitively, the Doob inequality tells you the following. If you want to control the trajectory of a martingale, it is sufficient to control the last term. I repeat. So, suppose that you have a martingale on 0 capital T. Okay, so a martingale that is continuous. If I plot the trajectories, okay, you have something. I start from 0. Okay, so I have continuous trajectories finishing at capital T. Okay, and in general, if you want to control such a mapping, you need to know all the values. Okay, with martingales, it will be sufficient to know the final value. It's not that surprising because you know for a martingale that mt is equal to the conditional expectation of m capital T given ft. If you have t less than capital T, meaning that from the final value, you can recover all the previous one, taking the conditional expectation. So it's something that is intuitive, but the Doob inequality tells you that if you are able to control the second order moment of this one, it will be the same for all this one in a very uniform way. Okay, so this is my intuition, and now I state the result. Theorem 0.5.3, that is the Doob inequality. Doob inequality. Okay. So let mt be a continuous, important, so with continuous trajectories. Let mt be a continuous and square integrable martingale. Then I have the following inequality that the expectation, so then for all capital T belonging to R plus, the supremum over 0 capital T of mt square. So this one is less than the expectation of m capital T square with a constant that is optimal and equal to 4. So it's what we call the Doob inequality. And it's exactly or intuitively what I have said here. You are able to control uniformly the trajectory in the terms of the nominal 2, okay, only from the last term. Okay.
Why 4?
Hmm?
Where does the 4 come from?
Where the 4 come? The proof, okay, will take me 3 or 4 hours, I think.
Okay, I'm good.
So it's coming from somewhere, let's say. But we can prove that it is optimal. So I don't have the example in mind, but it should be possible for me to show you a martingale such that this inequality is an equality. If you are really interested in, okay, for the next week I can come back with the example. I don't have it in mind, but you can prove that there exists a martingale such that I have the equality. So the 4 is really optimal. Okay? It's really optimal. Okay. So why it is important? So more than the result, why this result is important for us. Maybe let's do the break now, and I will, the teaser, okay, why it is important. See you after the break. In fact, the way we are going to use this inequality in this course is only to equip the space of the continuous and square integrable Martingale with a norm that is, I repeat, easy to handle. Okay, it's what I want to. So I denote M2 of 0 capital T. It's a notation that we will use a lot in the chapter, from the chapter 2, in fact. So it's just the set of the continuous Martingale on 0 capital T that are square integrable. So it's the set of the MT T belonging to 0 capital T such that MT is a continuous and square integrable Martingale on 0 capital T. So continuous, square integrable, and Martingale. Okay. And the idea is to equip this set with a norm, flexible norm. Okay. The idea is that, what is a norm? So when you have E, that is a vector space, what is a norm on E? So this mapping from E to R plus is a norm is what? 2 points for a norm. Pas besoin de plus de maths. Okay, so I will put it in the end. So it's what we call, okay, separability of the norm. Norm 0 means 0. Okay, so norm of x is equal to 0 if and only if x equal to 0. 0, that is the neutral for the operation you have on the vector space. We call plus. Okay? Triangular inequality. I agree. And homogeneity. This one. If you multiply your vector by a lambda, the norm of lambda x that belongs to the vector space because it is a vector space is equal to the absolute value of lambda, the norm of x. So this is a norm. So the idea, so here I have a vector space. Why? Because if you do linear combination of martingales, you obtain martingales because the conditional expectation is linear. Okay. L2 is a vector space, so no problem. Okay, and continuous is preserved by linear combination. So here you have a vector space, and I want to equip it with a norm. Okay. And I say that from this inequality, I can equip this space with a norm that is That's simple. I define the following. For M belonging to M2 of 0 capital T, I defined the norm of M as the following. So the norm of M in M2 of 0 capital T as the expectation of M capital T squared. This one. So you see that before to see that it is a norm, okay, we have something that is that simple in the sense that you have a stochastic process, and in the norm you have only the final value of the stochastic process. So in fact that here, what is this one? It's just the norm in L2 of the random variable M capital T. So it's the norm of M capital T in L2 of omega AP. So it means that to handle this norm, we won't be more complicated than to handle by the norm of L2. Okay? So why I have a norm? In fact, only one point is a problem for me. Which one? Which one is a problem and why the other are not? For the homogeneity, no problem. Multiply, we will have lambda square, the square root, so you obtain the absolute value of lambda. Classical. Okay, so for the homogeneity, if you have a martingale, you multiply it by lambda, you have absolute value lambda that is outside the expression. So for this one, no problem. Okay, everybody? So if you put lambda here, lambda here, with the square, you have lambda square. You can remove it by linearity. You have the square root of lambda square, that is the absolute value of lambda. Okay? So homogeneity is okay. For the triangular inequality, but no problem, because I know that I have a norm here. So if you have the triangular inequality for the norm in L2 for M capital T, you will have it for what I have defined this way. So the triangular inequality is just a consequence of the Minkowski inequality in L2. Okay? Classical way to prove that a norm in L2 is a norm. The Minkowski inequality that is reminded in the beginning of the lecture. Okay? And in fact, the only problem is this one, a priori. Okay? The separability. That is, if my norm is 0, then I am 0. What is to be 0 for an element of this set? Okay? In fact, to be 0 means to be indistinguishable with 0. Okay? That the probability of the intersection of the T belonging to 0 capital T is such that MT is equal to 0. I want this probability to be equal to 1. So a priori, if I take this one, if my norm is 0, what can I say? So from my definition, I can say that M capital T is equal to 0 P almost surely. And why it is sufficient to conclude that from this one? Because if MT is equal to 0, I know that the expectation of the supremum of the square is 0, implying that M is indistinguishable with 0. So the double inequality here will be only used in this course in order to justify here that defining something this way is a norm on the set of the continuous and square integrable Martingales. And from now on, okay, when we are going to work with continuous and square integrable Martingales, we are going to work with this norm. Okay, something that won't be that complicated to do. Just the square root of the expectation of the square of the final value. And you will see that this norm plays a big role in the construction of the stochastic integral, that is the integral with respect to the Brownian motion. We are going to use this one deeply in order to build what we call the Ito integral. Okay? So keep this in mind. Okay?
Excuse me, I don't understand your last sentence. M is this result with 0?
Yeah.
Why with? From 0?
No.
Why with? What does it mean?
With, it's just the definition I have given to you. X is indistinguishable with y if the probability of the intersection that xt is equal to yt is equal to 1. Okay, just the definition. So I am indistinguishable with 0. Indistinguishable de 0. You have your lecture notes. Just 2 pages before, okay? You have the definition of indistinguishability before, before. Yeah. M and 0 are indistinguishable if you want, if you prefer. M and 0 are indistinguishable. Just meaning that, I repeat, more important than the way to write, the probability this one, okay? And I have this because if this one is 0, I have the expectation of the supremum of the square that is 0, and so uniformly in T, okay, you have something that is 0 in L2. So that's why I am indistinguishable with 0 here. You are 0 for the product measure here, because you have the supremum inside the expectation. Okay, so you need to keep this in mind because it's something that we are going to use. So I just finished this part with a little proposition. Half of the proposition, yeah.
Dans les notes, j'ai marqué que M carré, c'est un ensemble de classes d'équivalence.
Ouais.
Du coup, là, c'est les classes d'équivalence.
Alors, in the notes, okay, it's exactly the following. So my idea was not to insist on little technical things, but if you speak about this, let's speak about this. So for example, if you take the space LP, okay? If you take the space LP, if you have two elements in LP, the notion of equality, okay, is the almost sure equality here, okay? X is equal to y is equivalent to the fact that the probability that x is equal to y is 1, okay? So if you remind, you know that this space is complete, okay? But if you remind the definition of the completeness, okay, when I am complete, it means that any Cauchy sequence is convergent, okay? And if you want such a property, you need to have something that is very important if you want to say something concerning the limits, that is the unicity of the limit, okay? The problem is that if you take, let's say, the convergence almost sure here, if xn converges toward x p almost surely, if you replace x by y, it works. So it means that it's something that you do in general without problem, forgetting that one time in your life you have seen this. That is, when you consider a random variable x, in fact it's not a single random variable that you consider, but in fact it's a class of random variable, all of them being equal p almost surely. And what we call x, it's a representative of this class. Okay? And why I need it? Because if I want LP to be complete, I need to consider all the random variables that are equal p almost surely together are in fact one thing and only one element if I want the unicity of my limit almost sure. Here it's exactly the same thing. It's the proposition I will state just after. So I will state that M2 equipped with this norm is a space that is complete in fact. And if I want it to be complete, I need the unicity of the limit. And if I want the unicity of the limit, for me, in fact, what I consider as a continuous and square integrable martingale is in fact not a single element, but the representative of the element of all the martingales that are indistinguishable with this one. Okay? I am not sure that it is necessary to enter in too much details for this one, because what you do naturally for LP, do it naturally for this set, and it will be exactly the same. Okay? In general, okay, we think about a random variable not as a single thing, but as a set of random variables, all of them being equal p almost surely together. Because in some sense, we remove all the negligible sets. We don't mind about negligible sets when we do probabilities. Okay? So it's the way we do. Is it clear? I don't want to spend too much detail on this, okay? But the idea is that you do exactly the same than for LP, and in general for LP you forget this. Huh? You use random variable as usual, okay, and it will be okay like this. Okay. So I have this one, so I have a norm, and the last little result concerning the part concerning martingales is the following proposition, that is proposition 0.5.6. I have two statements. The one that I have already proved saying this, that, okay, what I have defined this way is a norm on M2 of 0 capital T. And even here it's exactly what you have. In the definition of a norm, you have equal to 0, x equal to 0, but what is the meaning of x equal to 0? Here, p almost surely equal to 0, so it means that you identify x and 0 if p of x equal to 0 is equal to 1. We do exactly the same for the martingales. So it's a norm on M2 of 0 capital T, so it's something that I have proved just before, what I have erased here. And the second part, that is M2 of 0 capital T equipped with the norm here is a complete, or is an Hilbert space. So Hilbert means that you have a scalar product and that you are complete. Okay? So the scalar product here is not difficult to find. Okay? The scalar product between two martingales will be just the expectation of the product of the final value, because you have here a norm, in fact, that is a linear form, quadratic form. And to prove that it is complete. Well, it's a little bit technical. I want to do the proof, but you need exactly what I have said before, that two martingales will be equal if they are indistinguishable. And here, typically also, if you want to prove this one, so you take a Cauchy sequence and prove that it is convergent. If you want to do this, you need that your filtration is complete, that is, it contains the negligible sets in order to have this kind of unicity. Okay? So I have proved this one from the Douve, okay? Let's say that I have this one. Just keep in mind that when I will work with this space, okay, if I consider a Cauchy sequence in the sense of this norm, it will be convergent. Convergent and Cauchy will be equivalent in this space. And I will have a geometry coming from this scalar product. And it will close the part concerning martingales. So now we are going to do the end of the chapter. So that is more a general remark, okay, and a little exercise. And I will make you work a little today to change. So it's what we call the Radon-Nikodym theorem. I will just state it, also a complicated theorem to prove, really. But I just want to give you the intuition and just to show you that this is this theorem that is below the definition of the conditional expectation. If you remind, okay, when I have defined the conditional expectation, there exists a random variable such that I have said to you that later on I will show you that the existence of the conditional expectation is a consequence of something, this something being the Radon-Nikodym theorem. Okay? So, let's see some definition and after the theorem. In fact, once again, it's something that you use without knowing it in details in general. It is something that is at the basis of all the random variable with density that you work with, in fact. Okay? So may I erase everything here on the board? If you don't have questions, okay? So I erase everything. And we start the last part. And I think that I will just start the next chapter next week. The chapter concerning Brownian motion. So next week, okay, I will define Brownian motion. I will see some equivalent definition. I will prove the existence of the Brownian motion. We are going to do its construction. And we are going to start to study its properties, the martingale properties of the Brownian motion, the properties of its trajectory, the quadratic variation, and the Ito formula for the Brownian motion. Okay, so it's what we have to do in the chapter 1. But to conclude with the chapter 0, okay, the following. Radon-Nikodym theorem. Before, I need some definitions. We are going to state it in the framework of probabilities. It's something that you can extend for other type of measure, but in this course I will do probability, so I will consider probability as measure with a total mass that is equal to 1, okay? It's the way we are going to state the things. So let P and Q be two probabilities. The only constraint I have is that they have to be defined on the same sigma algebra related to the same universe. So two probabilities defined on omega A. It means that P and Q are from A into 0, 1, where A is a sigma algebra having omega as a universe. So P of omega is equal to Q of omega is equal to 1. And then P and Q fulfills the definition of the probability. Okay, so 3 definitions. Maybe I will write here. So we say that P is absolutely continuous with respect to P to Q. So P is absolutely continuous with respect to Q. The way to write is this one. P less than Q with this symbol, okay? Double less. Then, so P is absolutely continuous with respect to Q if for all A belonging to calligraphic A, Q of A equal to 0 implies P of A equal to 0. And that's why you have less. If Q of someone is 0, then necessarily P of someone is 0. Okay? So this is the meaning of being absolutely continuous with respect to Q. Okay? So if someone is negligible for Q, it will be for P. Okay? Second definition. P is equivalent with something that is important in finance. Here, equivalent to Q. You have the notion of equivalent Martingale measure. The probability equivalent to P that make the actualized value of the risky asset a Martingale under Q. Equivalent is this one. P is equivalent to Q if, so, and we write P equivalent to Q if for all A belongs to calligraphic A, in fact, P of A equal to 0 is equivalent to Q of A is equal to 0. So it means that in this situation, Q and P are equivalent if P is absolutely continuous with respect to Q and if Q is absolutely continuous with respect to P. Okay? And the last one, to be totally exhaustive, okay? P and Q are singular, and we use the orthogonality symbol, P orthogonal to Q, if what? If there exists an A belonging to calligraphic A, such that P of A is equal to 0, and Q of A is equal to 1. So something that is really different, okay? You have one set with proba 0 for one and one for the other. Okay? Do you have in mind examples of probabilities that are equivalent and probabilities that are singular based on what you know? You have a lot, I'm sure.
Of the singular, the negligible set with respect to the rest of the sigma algebra, maybe?
I want an example of such a P and such a Q. Concrete example. So you have several ways to build this, but in the classical things you know, that is by classical things, what are the classical probabilities you know? In general, they are the classical distribution of classical random variables. So you know, in the discrete case, uniform, binomial, Bernoulli, geometric, Poisson. In the continuous case, you know a lot. Uniform, exponential, Gaussian, chi-square, I don't know, gamma, beta, and so on.
On prend une mesure de Dirac.
Ouais.
Enfin, on prend deux avec des supports disjoints, ils vont être transverses.
Je suis d'accord pour ton exemple, c'est pas celui que je vais utiliser, mais il est bien. Ou Dirac masse. with disjoint support. Perfect. And in general, it's what we have to have in mind because it is the simplest example of something that is of two probabilities that are singular. Okay? But just in order to use things that are more common for you, if you take for P, let's say a poisson, and for Q, a Gaussian. Okay? The Poisson distribution, and for Q, a Gaussian distribution. Which capital A you will have to take in order to fulfill the small c? Are you able to give me one set such that P of A is 0 or P of A is equal to 1 and Q of A is 0? What is the support of a Poisson distribution? What are the possible values for Poisson? N? Okay. Take N. You have P of N that is equal to 1. Okay? Because the only possible values are the element of capital N. Okay? And if you have a Gaussian, you know that when you have a density function, the probability to take the value 1 point is 0. If you do this in a countable way, it will be 0 also. For all the random variables with density, if you take a countable set, the probability of this countable set will be 0. For sure. So you have here an example of two probabilities that are singular. So when I say that it's something that you know, it's in general in the course of probability, you have the case discrete continuous, but you have the case where they are singular. Okay? And all the discrete random variables are singular with all the continuous one. Mm-hmm. An example of two that are equivalent? Continuous, and I don't understand.
And we say that like just like this, we take it at 1 point.
Take it at 1 point. So I just take the beginning of what you said. Two continuous. If you take, for example, an exponential and a Gaussian, are they equivalent? If you take an exponential and a Gaussian, are they equivalent? I know. Because the support of the Gaussian is all R, while you know that the density of the exponential is 0 for strictly negative things. But it should be possible for you. Okay, but to find one that is 0 for the exponential, you just take an interval included in R minus that will have a probability that is strictly positive for the Gaussian. Okay, but two other equivalent. So if I take my example, I can find two that are equivalent. You can take, for example, I don't know, an exponential and a gamma, it works. Exponential and gamma works because they have the same support. But if I want to take something that's a little bit less complicated, let's say, you take two different Gaussians. You take two Gaussians with different parameters, you are sure that they are equivalent because the support of their density function are all R. Okay, so for B, I take two different Gaussians are equivalent, or exponentially gamma. Okay. And in fact, when you have density function, you just have to have a look on the support of the density, that is the set of the point on which the density is not 0. If they have the same, they are equivalent. And you see that in my examples, okay, here here I consider continuous random variables that have a density with respect to the Lebesgue measure, let's say. Okay? And in fact, it's the aim of the Radon-Nikodym theorem that tell you the following. Once again, here it's a theorem that is not that easy to prove. You have to come back to the very beginning of measure theory in order to prove this result. Okay, it's something that I won't do, but I just want to remind you that in my framework, if P is absolutely continuous with respect to Q, okay, if P is absolutely continuous with respect to Q, I can say the following. So P is equivalent to Q if and only if there exists Z belonging to L1 of omega A Q, okay, the Q that is this one here, with Z positive, and for all A belonging to calligraphy A, P of A is equal to the expectation under Q of the indicator function of A. We have this one. In other words, okay, Z is the density of P with respect to Q. So this is the meaning of the Radon-Nikodym theorem. The Radon-Nikodym theorem will tell you that if you have P that is absolutely continuous with respect to Q, in fact, this probability has a density with respect to Q, and my density is Z here. This is the aim of the theorem. And it's a theorem that is not that easy. So one side is very simple. This one is very simple. If you have this one, for sure, if Q of A is 0, okay, so you have this one, okay, if Q of A is 0, it means that this random variable is 0, Q almost surely, so its expectation is 0, and so P of A is equal to 0. So this side is very obvious. This one is a little bit complicated to prove because you have to build one Z that works, okay? I want to do this proof for sure, but the idea is to have this one. And just a remark that I will write just below here. So, notation of this one, we write Z equal to dP over dQ. So notation to write the density of P with respect to Q. Okay? Density of P with respect to Q. This one. Where this notation is coming from? From the fact that P of A, you know that P of A is written as the integral of the indicator function with respect to P. Okay? This one, you agree? I have this. But using my notation here, if I write the thing symbolically, I write dP as dP over dQ times dQ. And you have exactly this, because dP over dQ is Z. Okay? So that's why we use the notation dP over dQ for capital Z. So in other words, I repeat, what you have to keep in mind for this course is that if P is absolutely continuous with respect to Q, P has a density with respect to Q in the sense that we have this. In order to compute P of someone, it's just the expectation under Q of the indicator function of A multiplied by a random variable in L1 for Q. And I repeat that I introduce this notation that is coming from, let's say that I have the right to write this, that is meaningless, but just symbolic. This is P of A. If I introduce over dq and multiply by dq in order to make them equal, here you have the z. And if you have z here, you recover exactly this expectation. If they are equivalent, it's a remark. So suppose that we have more than to be absolutely continuous with respect to. Both of them are. But in terms of the density, if I'm in this sitting, okay, the only thing that changes is that I suppose that z is strictly positive. If the density is always strictly positive, then they are equivalent. So I repeat, here I have stated the Radon-Nikodym theorem, that is for the characterization of what is to be absolutely continuous with respect to Q. The Radon-Nikodym theorem tells you that to be absolutely continuous with respect to Q means that in fact you have a density with respect to Q. Okay, a density that is just something that is positive with an expectation equal to 1. It's the definition of a density. Okay. I said that if you want them to be equivalent, okay, you need to increase a little the hypothesis concerning the density. So you have a density, but this density is in fact always strictly positive. Okay. So it's exactly, if you take the example of two Gaussian distribution, both of them have strictly positive density everywhere, and you are able to express the density of one with respect to the density of the other, just multiplying and dividing by the same quantity, and it's possible to do because my density is always strictly positive. Always strictly positive. You are not able to do this with an exponential, for example. Okay. So I have this one. I don't want you to know more under this topic, and you will see that in mathematical finance, okay, I don't know if someone followed the course of arbitrage with me. No? Yeah, excuse me. With the mask, it's complicated to recognize, but it's what we use every time, because at the end, okay, we start from a probability that is supposed to be the probability, the real probability that we don't know. But in fact, in order to compute prices, it's exactly what we are going to see at the end of this course, it's not necessary to know P, but to know another one that is explicit, okay? And that will be used in order to compute prices. What we call an equivalent Martingale measure that is equivalent to the historical one, and so that will have a density with respect to the historical one, a density that will be perfectly known. And you will see this in the chapter 3. It's what we call the Girsanov theorem that will give you the density of what you want. Whatever, okay? Here, just have this one in mind. If P is absolutely continuous with respect to Q, I can write this, okay? And now, I want you to work a little, and you are going to do by yourself the exercise 0.6.1. Okay. So correction of the exercise. So why we can suppose in my statement here that x is positive. So it's something that is very classical, and you have already used this argument. Typically, if you have built the Lebesgue integral, it's a classical way to build an integral. First, build it for positive mappings, and then to use this little trick to prove that it works for everybody. I have a general random variable. I say that it's always possible to write it as the difference of two positive random variables. How to do? You remind? It's what we call the positive part and the negative part of something. I can take the maximum between 0 and x. Of course, I don't have this equality. I have this equality only when x is positive, okay? But minus the maximum between 0 and minus x. If x is positive, this one is 0 and the max is x. And when x is negative, this one is 0 and this one is what? Minus x minus, so I have x. Okay? And this one is what we call in general x plus, and this one x minus. It's something that you can keep in mind. Okay, sometimes it may be useful that you can write any mapping, and a priori also any random variable, as the difference of two positive mappings. Okay? And why, if I have this, it answers my question? But because suppose that the conditional expectation, you are able, so suppose that the conditional expectation of x plus given j and the conditional expectation of x minus given j are well defined. What will be a natural candidate for the conditional expectation of x given j? Suppose that these one are okay and fulfills my definition. That is, if I replace x by x plus and x by x minus, I have this. And that I want to define this one. How to define this one from this one? Have a look on what you have here. You have x that is equal to x plus minus x minus. Okay? How can you define the conditional expectation of x given j if the conditional expectation of x plus given j and the conditional expectation of x minus given j are well defined? Yeah? But what do you want to do instead of this? Yes, of course. I don't have a choice. I have this, and you can check that. It's easy to check that if you have the good property for the conditional expectation of x plus given j, the good property for the conditional expectation of x minus given j, this one fulfills exactly what you want because of the fact that x is equal to x plus minus x minus. Okay? So it means that when you want, if you want to define the conditional expectation, you can restrict yourself to prove that in my results here, x is positive. And you will see that it will change a little the things. Consider that it is positive. And keep in mind this argument because it's something that is often used in probability or in measure theory. To decompose the mapping as the difference of two positive ones. Okay? That are this one. They have a name. They are so called. Okay? Do you agree what I have written? So now I suppose that my x is positive. And the idea will be, so positive will mean that I will be able to define something that is like a positive measure, something like this. Okay. So I consider the following. I define Q from A into here R plus for the moment, okay? That is defined this way. Q of A is the integral over A of x dp. Or if you prefer, the expectation under P of indicator function of A. Okay. And now X is supposed to be positive. That's why I say that Q takes values in R plus. Okay. So what I want you to prove is that Q is bounded, first. And secondly, that Q is a measure that is positive measure, that is something that fulfills the sigma additivity property. If you have a sequence of pairwise division set, Q of the union is equal to the sum of the Q. The meaning of the question. So Q is positive for sure because X is supposed to be positive, so I have the integral of the positive mapping. I want you to prove that Q is bounded and that Q is sigma additive. And I repeat, meaning that if you have a sequence of pairwise division sets, Q of the union is equal to the sum of the Q. Why Q is bounded?
Something over A.
Hmm?
It's an integral over A.
So?
A is an integral, no? So,
No, Q is bounded means that Q of A is less than someone for any A. What you say me here is that Q is well defined. Q bounded means that there exists an M belonging to R plus such that for all A belonging to A, Q of A is less than N. It's alpha of a line to prove this. Why I am bounded? So you have the integral, okay, so Q of A is the expectation under P of the indicator function of A, X. X being positive, okay? Positive and in L1. So I can say that this is less than the expectation under P of X. So you have your bond here. Okay? Nothing to say. Because X is in L1, okay, you consider the integral over A. The integral over A of a positive mapping, okay, is something that is less than the integral over omega. That is the wall expectation. So Q is bounded here. For the sigma additivity, if I consider a sequence of pairwise disjoint sets in A, I want to deal with Q of the union, and I want to prove that it is the sum of the Q. Why I have this? I take my definition and I see what happened. Okay. What is Q of the union? Q of the union is just, okay, what? The integral of this one that I can write as the integral over wall omega of the indicator function the union x dp. What is the indicator function of the union if you have a sequence of pairwise division set? Yeah. Indicator function of the union in the case where I have a sequence of pairwise division sets is equal to the sum of the indicator functions. Since they are pairwise divisions, okay. What do you want to do now? Linearity is for a finite sum. You are not very far from this. But it doesn't work in general. It will work because I have a particular hypothesis here. You can see it in two different ways. Alors, en anglais, in French, we call it Bepo-Levy theorem. Et en anglais, c'est monotone convergence theorem. No? Yeah. Well, in both cases, what you have here, you have something that is positive. From the course of probability, you have result that is called the monotone convergence theorem or the Bepo-Levy theorem that tell you that if you are in this situation, you can switch the sum and the integral. It's the first way to see. Monotone convergence theorem. Second way to see, that is for me a little bit simpler, but it's something that you handle more. You have just an example here of the use of the Fubini-Tonelli theorem. The sum is just an integral, a particular case of an integral. You can switch between both of them, and I have no hypothesis to fulfill because I deal with positive things. Okay? So by Fubini-Tonelli theorem, or if you want monotone convergence, you can switch between two. So Fubini positive, that is the Fubini-Tonelli theorem, okay? It's the sum of the integrals. And here, by definition, it's just Q of A n. So you have here something that is sigma additive. Okay, we call it a measure theory. A measure that is bounded because Q is less than a constant. We are not very far from a probability because, okay, when you are bounded, okay, it is sufficient to divide by Q of omega and you obtain a probability this way. Okay? It doesn't change nothing to the sigma additivity. So I have a measure that is bounded, and in the question you have to prove that Q is absolutely continuous with respect to P. It means that if P of A is equal to 0, Q of A is equal to 0. Take the definition. If P of A is equal to 0, you have this one that is 0 P almost surely. And so its expectation is 0. And so Q of A is equal to 0. P of A equal to 0 implies indicator function of Ax equal to 0 P almost surely, implying that the expectation under P of the indicator function of Ax is equal to 0, implying that Q of A is equal to 0. You have a measure that is bounded and that is absolutely continuous with respect to P. Okay? So Q defined this way fulfills the fact that Q is a measure, that it fulfills the sigma additivity property, is bounded, and absolutely continuous with respect to Q, to P. Okay? The statement tell you that we have exactly the same if I restrict Q to J instead of A. That is, if I put J instead of A here. That you have all the proof on the board. I have never used on the board the fact that the sets I deal with are in A, nowhere. The only thing I have used is the fact that I have a sigma algebra. If you change J, A into a smaller sigma algebra, you have exactly the same thing. You can change nothing and you have, okay, I replace here J. I have this one, J. I have this one here and here. So in fact you have A belonging to A here, but you change A belonging to J, and you have exactly the same thing. Okay, so proving the fact for the biggest, that is calligraphic A, or the smallest, that is calligraphic J, it's exactly the same thing. So tell me if you are okay with this. And if you are, we are going to conclude, in fact, because we have everything now in order to prove that the conditional expectation is well defined. Okay, so tell me, may I erase, or do you have some question, or you want to finish the copy? Which board I can erase? This one? Are you okay or not? Tell me, I am not in wrong. Yeah, it's okay. I erase everything, if you're okay. I erase this one. So what I have proved, I summarize what I have proved. I proved that I have defined Q from calligraphic J into R plus. Q fulfills sigma additivity. Q is bounded. And Q absolutely continuous with respect to P. So I have stated the Radon-Nikodym theorem in the case of probability. Okay. But here I am, in fact, in the case of probability. So Q of omega or P of omega is not, or here P of omega is 1, but Q of omega is not necessarily equal to 1. But it is bounded, so it is sufficient to divide by Q of omega, and I have something that is a probability. So the statement of the Radon-Nikodym theorem with probability or with finite measure give rise to exactly the same thing. Okay? And what is the meaning of the Radon-Nikodym theorem? The Radon-Nikodym theorem tells you that there exists Z belongings to L1 of omega Jp such that for all J belongings to calligraphic J, Q of J is equal to the expectation under P of Z indicator function of J. Theta, it's not, there exists a G such that I have this. I just use the Radon-Nikodym theorem that I have the right to use here. Okay? I have this one. But what is Q of J? So I have erased the things here, but what is Q of J? Q of J, I remind you that it was defined this way. It's the expectation under P of X indicator function of J. But you have exactly what you need to have in the definition of the conditional expectation. Z is J measurable in L1 and fulfills the equality between the expectations here. So you have proved that in the case where X is positive, from my argument here, I have proved that I have the right to define the conditional expectation from the Radon-Nikodym theorem. And then, since I have seen previously that if I restrict myself to positive, I can extend to all the random variables, because a random variable may be written as the difference of two positive random variables. Okay? So in fact, this exercise is just a little exercise of probability if you know the Radon-Nikodym theorem. Okay? But to prove the sigma additivity or to prove other thing, okay, it's just basic results of probability. Okay, you have in the beginning of the chapter 0. So here, this little exercise shows us how to prove, if I admit the Radon-Nikodym theorem, that the conditional expectation exists. For the next week, I just want you to try to do by yourself. It's just a little computation, so less and less complicated than this one. The last example of the chapter 0, that is what I have called example 0.6.1. It's important. So I repeat, example 0.6.1 to do by yourself at home. Very short, a little computation concerning Gaussian distribution. You just have to remind what is the characteristic function of a Gaussian in order to do this exercise. And it will be the keystone of the chapter 3. Okay? We'll see you.